All right, welcome everyone to today's Munich AI lecture. My name is Daniel Kremers, and it's my great pleasure to introduce today's speaker. We have another very eminent machine learning researcher here with us today, and this is Professor Michael Bronstein from Oxford University. Maybe a few words before I hand over to Michael. He's a well-known researcher. He's a DeepMind professor of AI at Oxford University and also head of the graph learning research at Twitter. He's been many places. He's been at Stanford, at MIT, at Harvard. He's been at TU Munich as well as a Rudolf Diesel Fellow, and he's been at Harvard as a Radcliffe Fellow. He got his PhD in Israel at the Technion. And subsequently, he's been many places. He's been in Lugano, he's been at the Imperial College, and he's now in Oxford. He's won many awards and prizes, among these the Royal Society Wolfson Research Merit Award, the Royal Academy of Engineering Silver Medal. He's won 5 ERC grants and numerous research awards from Google, from Amazon, and others. I don't really want to list all the achievements he has done, but maybe on a more personal note, I've known Michael for many years now, from when he was still a PhD student, and what inspired me most is that Michael is one of the rare people in our community who is both an excellent scientist and academic, but also an amazing entrepreneur who has built a number of very successful startups and companies over the years, including InVision and including Fabula AI. And this, for me, has always been a great inspiration, that you can actually do both. You can actually develop amazing research, and you can assure the transfer into society. So it's a great pleasure for me and for all of us to have Michael with us today. He will be speaking today about physics-inspired learning on graphs. I would ask everyone to please switch off their cameras to reduce bandwidth and to mute themselves. Please refrain from asking questions during the talk because of the recording. We can have questions at the end of the talk. So, Michael, the floor is yours.
Thank you very much, Daniel, and thank you everybody for coming and for the invitation to be in Munich, even though virtually. I think it's a great place, and I have very fond memories when visiting for several summers as a fellow at the Institute for Advanced Study and being hosted by Daniel. So it's really one of the exciting experiences I've had. So I would like to talk about some of the topics that we've been working on in the past several years, and somehow to connect the dots between maybe apparently unrelated topics. And that's why the title is a little bit enigmatic: physics-inspired learning on graphs. So I would like to start actually, well, if we are talking about physics, I would like to start with a quote of a mathematician who had probably a profound impact on physics in the 20th century, and this is Hermann Weyl, who spoke thus poetically of symmetry. And he called it as wide or as narrow as you may define its meaning, this one idea by which we, through ages, try to comprehend and create order, beauty, and perfection. And I think it really recognizes and highlights the important place that symmetry has in science and in art. And it's been fundamental to the development of physics as well. So the term itself is geometric, right? So it's a geometric concept, and geometry, as you probably know, traces back at least to the ancient Greece, where it was first formalized by Euclid. And for more than 2000 years, the geometry that was developed by Euclid in an axiomatic way was the only one that was available. And we still study it at school as the geometry, right? Even though now we have slightly more broader choice. And what happened in the 19th century is that this monopoly of Euclidean geometry came to an end with the first successful construction of non-Euclidean geometries. And towards the end of the century, an entire zoo of different geometries emerged, and it was not clear exactly how they're connected, what actually defines in geometry, right? And there are many branches that somehow competed with each other. So a way out of this situation and a formalization of geometry was proposed by Felix Klein in 1872. He was a very young one. He was appointed as a professor at the University of Erlangen in Germany, I think only 23 years of age. And as it was customary at the time, and probably still customary in Germany, he was asked to deliver an inaugural talk that entered the history of mathematics as the Erlangen program. So actually in the talk, he didn't talk about research, he talked about mathematical education, but it was the prospectus, this little brochure that you can see, its cover here, is what captured his ideas. And the idea was quite revolutionary. So he suggested to consider geometry as a space plus some group of transformation. So in other words, he looked at properties of geometric objects that remain unaffected or invariant by an action of some class of geometric transformations described as a group. And this was a kind of algebraization of geometry. So probably the second one, first one was done by Descartes before that. And it brought completely new tools that allowed to, for example, classify and hierarchically organize different types of geometry. For example, Euclidean geometry could be associated with rigid transformations of objects, and affine geometry is something that is slightly broader, right? And then he argued that projective geometry that comes from the projective group is the one that should be used in physics. And indeed, these ideas were picked up. So Emmy Noether, she was his colleague at Göttingen, where he eventually moved. He just spent 3 years in Erlangen and then moved to Munich, to what nowadays is TUM, and then eventually to Göttingen. So she came up with also a very important insight in physics that is known as Noether's theorem, that you can derive conservation laws that before that were mainly empirical observation from fundamental principles of symmetry. So, for example, you could say that if you measure the energy in an experiment, and you do it many times, you would say that the energy doesn't change, so there is conservation of energy. But she showed that this can be derived under certain assumptions from the symmetry of time. And this idea basically became the foundation of modern physics. You can derive the entire physics from these very basic considerations. And in physics, it's common to distinguish between what is called external symmetry, the symmetry of space-time. So in this case, this is what is called the Poincare group, which gives rise to the Minkowski geometry of the special relativity, or the internal symmetries of the fields, and they gave rise to different types of interactions, such as electroweak or strong interactions. And this was tabulated in the form of the standard model. So this is almost all physics that we know nowadays that can be derived from considerations of symmetry. Now, in deep learning, we also have this zoo of different animals, and in this case, these animals are different neural network architectures that historically were developed for different types of problems or for different situations or for different tasks, such as convolutional neural networks that originate maybe in neuroscience, but were developed for image analysis, right? And they deal with grid structured data, or recurrent neural networks that were developed to analyze sequences, such as sequences of words, right? Natural language processing, or audio signals, or graph neural networks that were developed for relational data, such as chemical molecules. So apparently in this zoo, there is nothing in common between these different architectures, but what we try to do in geometric deep learning is to bring some common denominator, some kind of basic principles similar to the Erlangen program that allow us to derive these architectures from the notions of invariance and symmetry. And to do it, you can consider the fact that the data that your neural network is applied to comes from it often has some built-in geometric structure. So you can think of a data that lives on some geometric domain, and this geometric domain is equipped with a symmetry group. And on this domain, you have some signals, and the group acts on these signals through some group representation. So you can design functions that ingest these signals to respect in the right way this symmetry group, either in the form of invariance or in the form of equivariance. So in other words, the output of the function is independent on how the the input is transformed or is transformed in the same way. So the classical example, of course, are convolutional neural networks. So in this case, the domain is a plane or a two-dimensional grid. The group is the group of two-dimensional translations. The data are images that live on this grid, and the representation here is the shift operator. And convolutions are shift equivariant operations, right? So the convolution operator commutes with shift. And this is baked into a neural network architecture that is called convolutional neural network, but you see that it's a particular instance of this blueprint that you just need to select the right domain, the right group, and the right equivariant operation. Another example that I would like to discuss today are graph neural networks. So in this case, the symmetry group is the group of permutations that reflects the fact that the nodes of a graph do not have a canonical order. So they can be numbered in any arbitrary way. So basically, this group acts on the features that live in the nodes of the graph through a permutation matrix, and then we can design functions such as message passing that would be equivariant with respect to this transformation. Now, same way as we have in physics internal and external symmetries, we can also distinguish between symmetries of the domain and symmetries of the data in the deep learning context. And this is actually a new animal in the architecture or in the zoo of graph neural network architectures, what is called equivariant graph neural networks or equivariant transformers that are nowadays very popular in modeling molecules and also are used by DeepMind in their AlphaFold too. So the idea here is that in addition to the permutation symmetry of the nodes of the graph, you also the coordinates, right? So the features of the nodes represent some geometric coordinates. So this is a geometric graph that lives in three-dimensional space, right? Like think of a molecule where the nodes are atoms and edges are chemical bonds. So in this case, it is also meaningful to subject the graph itself, right? The coordinate of the nodes to some geometric transformations, some continuous transformations, such as the special orthogonal group, right? Or basically rotations and translations. So we can make message passing equivariant with respect to both transformations, right? The permutations of the nodes and their continuous rotations and translations. Now, why at all we are interested in graphs? Because they are a very convenient mathematical abstraction for systems of relations and interactions at all scales, from macroscopic scales such as molecules to gigantic scales such as social networks or different interaction networks that we see in biology. And graph neural networks were developed to analyze this kind of data. So in the basic setting, we can assume that the graph is just a collection of nodes connected by undirected edges. We have some d-dimensional feature vectors at every node. And the structure can be represented in the form of two matrices. So the matrix of the features of size n by d, n is the number of nodes and d is the dimension of the features, and the adjacency matrix that represents the structure of the graph. So there is a 1 at the position where there is an edge and 0 if there is no edge there. So one key characteristic here is that the ordering of the rows or the columns in these matrices is completely arbitrary. And if I order the nodes differently, I need to permute these rows and columns. And this is done by permutation matrix. So we have n factorial such permutations. Now, in terms of the tasks that we typically see in graph learning applications, there are two canonical tasks. One of them is predicting properties of the graph itself, right? And think of examples in chemistry where you have a molecule and you try to predict, for example, whether it can be dissolved in water. On talking about social network examples, you can, for example, try to predict who is a spammer in a social network. So in the first case, we are interested in functions that are insensitive to the way that the inputs are ordered, right? So no matter how I permute the inputs, the output should be the same. So this is an example of permutation invariance. In the second application, I want the output to be permuted in the same way as the input. So if I change the inputs in some way, I want the outputs to be changed in the same way. So we are talking about the case of permutation equivariant functions. And graph neural networks essentially combine these operations in the form of layers that are parameterized with learnable parameters depending on the task. And in the case of node-wise predictions, we output some embeddings or vector representations of the nodes. Or in the case of graph tasks, we also pull it into a single vector based on which we can predict the properties of the graph, for example, the molecule. So the way that graph neural networks work is by some form of neighborhood aggregation. So we start with a node, and look at its neighbors. So what is clear from this picture is that the node sees the neighbors, but it doesn't see any particular order, right? So basically it sees a soup of node features and edge features, right, if they are such. So if we want to aggregate this information, let's say in the form of a function that I call phi, we need to account for the fact that there is no canonical order of the neighbors. So in other words, this function must be permutation invariant. Now I can apply this function everywhere at every node of the graph, right? And this way I get an output that is a matrix of features produced by this message passing. And now it's easy to see that this function is permutation equivariant, because if I permute the inputs, the outputs will be permuted in the same way. So the choice of this aggregation function that I denote by phi really determines how the graph neural network architecture looks like. And we can distinguish between three broad classes of graph neural networks. The first one is called convolutional. So in this case, the aggregation, you can think of it as a summation, or maybe more general, permutation invariant operator that takes the neighbor node features, maybe transforms them, and then just sums them up, right? And this is used to update the feature of the node I, right? So in the simple case, these are just the coefficients of the graph adjacency. They depend on the structure of the graph, but not on the features. And the node-wise transformation in the simplest case can be just a linear transformation. So here you get a recipe for the simplest graph neural network that is called GCN, or graph convolutional network. Basically, it has two operations: node-wise channel mixing, so a linear transformation of the node features, and a diffusion, right, or some propagation of information on the graph that multiplies the matrix of features from the left side. So it is highly scalable. I think it's fair to say that all the industrial use cases are really these kind of architectures of convolutional type. And the folklore that is repeated from paper to paper in the field says that it works only in cases where the graph is homophilic. In other words, my neighbors are similar to me. And the reason is, the typical explanation that is given is that diffusion matrix, the adjacency matrix, acts as a kind of low-pass filter, right, that averages the features of a node with its neighbors. So if the features of the neighbors are dissimilar, we are basically will be averaging garbage, and it will become useless. So if I have time, I will show you that this is not correct. So this is actually not true, and the channel mixing plays a crucial role here. So there is an interesting interaction between the structure of the node-wise transformations and the graph propagation. So slightly more general flavor of graph neural networks are attentional networks. So in this case, we still have aggregation with some coefficients that depend on the features now. So these are attention weights. And in the most general case, we have a nonlinear function of bivariate, depending on two features of the node and of its neighbor, that can be regarded as a message that is sent from one node to another. Now, what is important about message passing is that it is formally equivalent to a class of methods in graph theory that are called graph isomorphism tests, or specifically the Weisfeiler-Lehman algorithm for testing whether two graphs are isomorphic. And this happens if the aggregation in message passing is chosen to be an injective function. And the Weisfeiler-Lehman test was published in 1968. It was actually believed to be a polynomial time algorithm for testing whether two graphs are isomorphic. So graph isomorphism problem is an interesting problem because its complexity is unknown. So it's known to be not NP hard, but on the other hand, we don't know whether there are polynomial solutions. So it's placed in its own complexity class called GI. And it is interesting actually that the motivation for this problem came from the domain of chemistry and the works of Romanian science George Vladuț, who tried to compare chemical compounds, and particular problem that he was looking at is information retrieval, trying to search a compound in a large data set by structural similarity. So essentially trying to test whether two graphs are isomorphic, or at least Weisfeiler-Lehman acknowledged him in their paper for posing the problem. So how does this test work? Basically, it starts with a graph that is colored, every node is colored in the same way, right, or attached to the same label. And it's a kind of iterative color refinement procedure. So every node looks at its neighborhood and then applies an injective function. You can think of it as a kind of hashing to this neighborhood, right, to the multiset of the neighbor features. And in this initial graph, we have, you can see two types of neighborhoods. We have blue node with 3 blue neighbors and blue node with 2 blue neighbors. So these will be hashed to different values and will become two different colors, right? So I can update the labels in the graph, and you can see that now the graph has two colors. I can apply the same procedure again, and now we have three types of neighborhoods, right? So we have green neighbor with one yellow and one green neighbor. So this will become, let's say, gray. We have a green neighbor, a green node with two yellow neighbors, and let's call the new label violet. And then we have another case of a yellow node with two green and one yellow that will become orange. And if I repeat the procedure again, then the colors will stop changing at some point, at which point we will output the distribution, the histogram. And the algorithm is built in such a way that it's guaranteed that if I give you a different graph that is not isomorphic, then, if I give you another graph and the distribution that is produced by this procedure is different, then I can guarantee that this graph is not isomorphic. But if the distributions are the same, we actually don't know. We can find simple examples of non-isomorphic graphs that the WL algorithm cannot distinguish. So it's a necessary but insufficient condition. And you can see why, because the way that it looks at the neighborhood of every graph, basically it looks at a BFS tree. And in this case, in this simple construction, you can see that these trees look exactly the same. So it even cannot detect triangles in the graph. Now, fortunately, in addition to this simple algorithm, we have an entire hierarchy of Weisfeiler-Lehman tests. So these were developed by Laszlo Babai and also independently by Eric Lander, who now is mainly known as geneticist and biologist, but he actually started his career as a mathematician. And there are different classes of graphs that will be indistinguishable by these KWL algorithms. So, for example, 1WL cannot distinguish regular graphs. For higher order, you have more complicated, strongly irregular graphs, or what is called CFI, Kiefer, and Immermann graphs that will be indistinguishable KWL graphs, so by KWL method. So the standard message passing, as I mentioned, is equivalent to the standard WL approach. There are generalizations that are equivalent to KWL that were constructed by Hagai Maron. So these are computation expensive, so they're not practical. They're good for proving theorems, but not really useful. And there are some other slightly more exotic methods, such as our recent collaboration also with Hagai, looking at a graph as a collection of subgraphs that are extracted by some policy. So in this case, you get complexity that is equivalent, at least asymptotically, to the standard message passing, linear in the size of the graph, but strictly more powerful than 1WL. So it's actually upper bounded by the expressive power of 3WL. Now, another common trick that is used in the literature is some form of positional encoding, or in particular structural encoding that we did with my students in a paper in 2020, is saying the following thing, that if we know that, for example, 1WL cannot count triangles, let's count them and provide them as node or edge features. So in this case, for example, I can count triangles or 4 clicks. And here we get an algorithm whose expressive power is actually outside of the standard WL hierarchy. And by the appropriate choice of these substructures, we can be at least not less powerful than any KWL. So meaning that there will be some cases that KWL cannot distinguish, but the standard message passing with structural encoding can. But again, there might be also cases to the contrary. What it also gives you is a kind of problem-specific inductive bias, because we know, for example, that in organic chemistry, in molecular graphs, cycles, right, or rings are important structures. So we can count them, and we show that this gives significantly better expressive power. Now, another problem that we see is that the standard way of doing graph neural networks, right? So the mindset of Weisfeiler-Lehman is to use the input graph to propagate information on it, right? And by doing so, you discover somehow its structure. But some graphs may be actually quite unfriendly for message passing, like the graph that is shown here. It has a bottleneck. So if I need to transfer features from the left side to the right side, I have only one edge through which I need to squeeze all the information. And this is not great, right? So information doesn't flow well. So in this case, the standard trick is graph rewiring. And this can be done in many different ways. So de facto, I think most of graph neural networks, at least the modern ones, do some form of graph rewiring, but it's in the form of neighborhood sampling, like the graph sage introduced by William Hamilton, or the diffusion of the graph topology, the Deagle paper introduced by the group of Stefan Günnemann here at TUM, or maybe some more exotic forms of rewiring based on the discrete analogies of Ricci flows or expander graphs. So bottom line is that we have a gap between theory and practice because the graph that we use to propagate information is not the input graph, and therefore we cannot really appeal to the analogy between the Weisfeiler-Lehman theory. So this theory is too rigid. We want something that is better and looks at the expressive power of graph neural from a different perspective. So just to summarize, if we look again at standard GNNs, so they stick to the input graph to propagate information. You can completely ignore the input graph and just consider every node of the graph as a set, right? Element of a set. So in this case, we get an architecture that is called a deep set or a point net. It's used in computer graphics very often for the analysis of three-dimensional point clouds. And in this case, there is no interaction between individual nodes of the graph. On the other extreme, we can say that every node can interact with every other node. So in this case, we have a fully connected graph or a complete graph that can be learned based on the task in the form of attention. So these are the famous transformer architectures, and graph rewiring sits somewhere in the middle. So we typically compute the new graph as a pre-computation and then use it to propagate information. Now, in the case of transformers, at least in the classical application in natural language processing, we actually do want to capture some permutation-dependent functions, dependent on the position of a word, let's say in a text. So this is typically conveyed in the form of additional features that are called positional encoding. So I can pre-color or attach some extra features to every node of the graph. And structural encoding is something similar that can be generalized to graphs. There are other examples, like for example, we can take the eigenvectors of the graph Laplacian and use them as positional or structural features. Now, it is also possible to start with the graph and lift it to some more complex topological objects, such as cellular or simplicial complex. So you can say, for example, that every cycle of certain size becomes a cell in this graph, right, in this object. And then we can do more interesting message passing that doesn't only send information between nodes, but it can also go up and down in this topological hierarchy. I mentioned already the subgraph GNNs. So in this case, we look at the graph as a collection of subgraphs with node-wise correspondence. And here we have a more interesting symmetry because we have two types of permutations. Permutations of the nodes in the graph, in the basic graph, and permutation of the subgraphs in this collection. So we have a product symmetry group. If we make message passing equivariant to it, we can show certain properties that are more expressive than the standard message passing. Also, what I mentioned, if we can treat the continuous features of the nodes, basically account for their symmetry, so we get equivariant GNNs or equivariant transformers. And again, these are very popular methods in computational chemistry nowadays. And finally, if we have graph with some rigid structures, such as a grid, we boil down to CNNs. So in this case, we have canonical node ordering, and we can do, instead of message passing, more structured way of propagating information that boils down to being classical convolution. So all these cases, you can say that we have more structure, right? Either the structure comes somehow outside, or we make it up, right? Or we lift the graph into something more complex in maybe a learnable way. And then this richer object allows us to do more interesting things with the graph. Now, just to compare these three different objects, right? So grids on which GNNs act, graphs on which GNNs act, and then simplicial complexes, right? Or meshes, maybe in the case of applications in computer graphics, on which some form of geometric CNNs act. So if we look at the grid, a grid is the most structured object, right? So if I take a node and look at its neighbors, we don't have any ambiguity, right? I can always say that I have a neighbor on my top and a neighbor on my left, and so on. In a mesh, we have a kind of halfway situation, right? I can choose arbitrarily the first node and then order the rest of the nodes in clockwise orientation, for example, right? But the choice of the first node is arbitrary, so it's defined up to rotation. And finally, in a graph, it's defined up to arbitrary permutation, right? So I can permute the neighbor nodes in any way. So in a sense, graphs have the least structure. Now, the second thing that we observe is that grids And meshes can be considered as discretization of some continuous objects. So grids can be considered as the discretization of the plane. And meshes can be considered as discretization of some surface, right, a two-dimensional manifold. We don't have immediately a continuous model for graphs, right? So graphs are somehow inherently discrete. So what we'll try to do is to change this mindset and consider graph neural networks from a different perspective. We'll try to consider them as physical or physics-inspired systems. And by discretizing these systems, we will get back either classical GNNs or maybe some insights about how to make certain educated architectural choices in graph neural networks, or maybe completely new exotic architectures. So the way that I would like you to think now, from now on, about graph neural networks through these physical metaphors, think of GNN as a dynamic system. So dynamic system where every node in the graph is some particle that evolves in some space, right? So it's governed by this differential equation that is parametric. And if you discretize this differential equation in time, right? So this every step in time corresponds to a layer in your deep neural network. And the graph can be considered as a kind of coupling function, right? So these particles are not evolving completely on their own. So there is some dependency between the rows of these matrices in this system of differential equations. And in some cases, we can also consider the graph as a discretization of space. So we can think of graphs embedded in some continuous space. So the standard approach to graph neural networks is to write down the evolution equation, discretize it, and parameterize every step, right? So this is how graph neural networks look like, right? What we try to do and what we can do differently by with this physical mindset, we can take an energy functional and parameterize the energy functional, and then derive the evolution equation as a gradient flow. So it's a particular type of evolution equation that looks like the negative gradient of some energy. And this gives us better interpretability because in many cases we know what this energy measures, right? What it represents, and we can say that the energy decreases along the flow, along the evolution. So certain properties become maybe more manifested in this process. So one example is some extension of the Dirichlet energy. So the classical Dirichlet energy in physics measures some form of smoothness. So here we have slightly more complicated energy. So it's quadratic energy in the node features. And again, you can think of it as an energy associated with a system of particles, right? Nodes of the graph, parameterized by these two matrices, omega and W. And we have two terms here. So the external term acts on all particles, and the internal term that represents pairwise interactions between nodes along the edges of the graph. And if we look at the structure of the matrix W that performs channel mixing, right? So that's the channel mixing matrix in graph convolutional networks. Its positive eigenvectors induce attractive interactions, and negative eigenvectors induce repulsive interactions. And if you write the gradient flow of this energy, you see that the matrices omega and W appear in symmetrized form, so we can assume them without loss of generality to be symmetric. And you can also see that they're time independent. So when we discretize this, right, so when we'll convert this into a neural network, this will mean that we have shared parameters across layers. So just to give you an idea of how it might look like, so here's a graph, right, and the coordinates here represent the features, the coordinates of the feature vectors of the nodes. The colors represent different labels, and you can see that here we have an example of the horizontal direction along which repulsion happens and vertical direction along which attraction happens. And you can see that even though this graph is heterophilic, where the nodes of different color are connected to each other, nevertheless, we can separate them by this evolution process. So as I mentioned, the neural network itself is derived by discretizing this gradient flow. So it gives rise to residual convolutional type GNN with symmetric weights. And it's important to stress that symmetry doesn't diminish expressive power. So there are some universal approximation results for neural networks with symmetric weights. And what is important that the weights are also shared across layers. So the way that it's used, we start with node features on the graph, right? And let's say that the task is node classification. So we optionally and do some nonlinear encoding of the node features, apply a linear gradient flow, and then read out with some decoder. So it's a residual architecture, linear, nonlinear activation, and symmetric shared matrices. And as opposed to the standard way that the GCNs, right, the graph convolutional networks are used. So in GCNs, GCNs are non-residual, they have non-symmetric weights, they have different weights per layer, and they have nonlinear activation. So somehow all this is deemed to be important, that every layer is parameterized separately, and that the layers are activated by something like ReLU. So the downside, GCN is not a gradient flow. It has the number of weights is linear in the number of layers. In our case, because the weights are shared, it's independent on the number of layers. And what is most important, that we actually show that GCNs, because of the lack of residual connection, can induce only low frequency dominated dynamics. So they tend to oversmooth. And as a result, they work only on homophilic graphs. Whereas neural networks that are derived from the gradient flow can induce both low and high frequency dynamics. And as a result, they work on heterophilic graphs. And here is an example that you can see here, that we have a synthetic data set where we can control the level of homophily. And when the homophily is low, then we have an example that looks like the one on the left. So nodes of different types are connected together. Whereas if the graph is homophilic, then only similar nodes are connected together. And here we can do two extremes. So we can apply the GCN, right? So that works very well in the case of homophilic graphs, but when the graphs are not homophilic, of course, we average completely irrelevant information. And as a result, the performance degrades dramatically. As another extreme, we can completely ignore the graph structure, and we can apply just node-wise multi-layer perceptron. So we just consider the features as a standalone vector. It works well in case of heterophilic graphs, again, because it ignores these graphs, but it doesn't take advantage of the graph structure in the homophilic case, right, which affords this high performance to GCNs. So the framework that they described, the gradient flow approach, allows to take advantage of both worlds, right? So it works well in the homophilic case as well as in the heterophilic case. So I think this busts the myth about convolutional type graph neural network architectures being unable to deal with these kind of settings. Now, I know that I'm running out of time, so let me just show one more exotic example of how graph neural networks can be derived. So in this case, we start with a graph and we make it into a more complicated topological object called a cellular sheaf. So if you think if you want a parallel to differential geometry, so a manifold is purely topological object, right? So it has only the notion of neighborhood, right? So I can tell who is next to me, but not how distant it is from me, right? Or at which direction. So in order to assign some geometry to a manifold, this can be done in the form of what is called an affine connection. So basically I show how to transport vectors from one tangent space around one point to a nearby point. And if the manifold is equipped with Riemannian metric, then there is a special connection that is called the Levi-Civita connection that is compatible with the metric. So a little bit similar on a graph, we can say that every node and every edge has an attached vector space. And we have some linear transformations from a certain class, so certain type of matrices that transport vectors from one node to another, or from one node to an adjacent edge. And this way we endow the graph with geometry. And if, for example, we run a diffusion equation on this cellular chip, right, where all the differential operators are now defined accordingly, we can look at what happens in the limit, starting with some initial conditions. And in particular, we can look at node classification problem and see how many node classes can we separate by diffusion if we restrict our sheaf to be in a certain class. And here the results are interesting. So for example, if we have homophilic graphs with two node classes, so in other words, a binary classification, then very simple one-dimensional with symmetric transport maps, right? In other words, that's the classical example of just weighted graph, can separate these classes. But if the graph is heterophilic, then suddenly it doesn't work. So we need to introduce non-symmetric restriction maps in the sheaf. So in other words, we need to treat differently whether the from its neighbors. If the number of classes is greater than 2, then we need to go to higher dimensions, and there we can also study some further restricted maps such as orthogonal transformations that make interesting connection to what is called connectional Laplacians or vector diffusion that was studied by Zinger about 10 years ago. So what we gain from these physics-inspired GNNs, I think it's a new perspective on all problems, potentially new architectures. So first we can formalize existing GNNs as discretized versions of these dynamic systems, possibly more efficient solvers, such as multi-step, adaptive step size, implicit multi-grid methods. So all these methods have actually been widely used in image processing and computer vision, PD-based and variational techniques in the past 30 years. All these almost disappeared with the advent of deep learning, but I think it's these are very good methods that probably need to be given another life. And well, Daniel is a prominent example of people who have contributed seminal works in this field, probably around 20 years ago. So what else do we gain? We also gain principal architectural choices, such as, for example, residual connections, symmetric weights or weight sharing, theoretical guarantees about stability and convergence, some form of expressive power, and also deeper links to other fields that are probably less known in graph literature, such as differential geometry and algebraic topology. And of course, we don't necessarily need to limit ourselves to this kind of diffusion type equations. We can also look at higher order differential equations, such as oscillators. So this was a paper that recently appeared at ICML, collaboration with Konstantin Rasch and Sid Mishra from ETH Zurich, where we studied wave type equations, graph coupled oscillators. So I know that I'm probably quite out of time, so I will stop here and thank you for your attention, and we'll be happy to answer any questions.
Thank you, Michael, for this wonderful presentation. Thank you also for the great visuals. I love your presentations because the slides are often very visual, including the last one here as well. Do we have questions? Maybe I'll start with a question myself. I like this idea of looking at graph neural networks as a form of discretization of something continuous. And you said there's different ways to discretize. You can discretize the differential equation. You can discretize the energies. Typically, when you look at different forms of discretization, that entails questions of the form of do you guarantee certain continuum limits? So let's say if your discretization gets increasingly finer, what properties of the continuous underlying theory are preserved? And in that sense also, what conservation laws do you have? Are properties that are conserved in the continuum also preserved in the discrete setting or not? Can you comment a little bit whether these questions play a role here?
Yeah, I think this is a very good question, also a very deep question. So if you know in your problem that certain properties are important, you can certainly encode them in the form of conservation laws, sometimes maybe giving rise to a kind of pseudo-physical system that doesn't correspond to real world physics, right? So you can invent new physics and make it into this kind of crazy system that does something and preserves certain properties, certain symmetries, but it's not realistic. So I should say that, well, in some situations it's justified, right? Especially if you have some prior information about your problem, right? And you have certain properties that you want to preserve. In general, I think this is somewhat different. What the approach that we are taking here is different from physically correct neural networks, right? Or physically informed neural networks, what sometimes it's called, where you try to use graph neural network to solve some physical system or a neural network in general, right? Where you try it as a kind of compressed way of replacing numerical solvers for fluid dynamics systems or things of this kind. In this case, we use it just as a metaphor to parameterize the space of solutions that a graph neural network can reach. And we again the reason for doing it, because we can say theoretically something better, or maybe we have a better numerical scheme that applies in this case, rather than having a completely arbitrary message passing that can be anything. We can say that if we make these particular choices, this is the kind of properties that we can guarantee that in many cases are sufficiently rich and good and important. And what we gain is, for example, the less parameters, shared weights, right? So more lightweight architecture with certain guaranteed behavior.
All right, maybe, I don't know. I'll ask another question. So please, anyone who has questions, please just raise your hands or speak up. I'd have another question, and that is somehow the graph neural network is at this point often considered as the methodology to solve all problems in the world. Do you see that there are problems that do not fall in the class of solvable problems where basically the framework of graph neural networks is too limited?
Yeah, of course. So anything that has non-pairwise interactions, for example. So when you have, well, the physical analogy would be multi-body potentials, right? So you have a system where your particles interact interact in a different way when basically there are more than just two particles. And this is common in different situations. So this can be modeled as either as hypergraphs or as cellular or simplicial complexes. So you know a priori sometimes that there are certain structures that have a meaningful that have some meaning in your application, like cliques in social networks or rings in chemistry.
Yeah, that's interesting. There is a related question from YouTube. Are there GNN models that predict the state of the system at any interpolated time between I times tau and I+1 times tau? So in some sense, going into there is an underlying continuous representation, I guess, can we use the GNN model to predict things that are in between?
Yeah, so I think probably it's slightly different. So in this case, the time itself, so the pseudo time, right, that we use here is probably not that meaningful on its own. But there are situations when you actually have a dynamic graph, right? So you have a system that on its own is dynamic. So basically the conditions of the systems are changing. The social networks are a good example, right? So when you have new users that appear or are connected to each other, so new edges created or destroyed in the graph, or new nodes as well. In this case, this can also be modeled in continuous time, and there are some architectures like we developed one that is called temporal graph networks that actually allow us to make predictions, for example, about nodes. Basically, you have a time-dependent embedding of the nodes, and you can predict whether an edge will appear at some point of time.
Another question from YouTube. You spoke about a continuous notion or discretization in time, but also hinted at a notion of continuum limit of graphs in the space of dimensions, similar to the discretization of a mesh, the mesh as a discretization of a surface. Can you comment on that?
Yeah, so it's also a broad question. So there are some models, first of all, so there is an entire, I think, even field that is called network geometry that tries to derive graphs, right, or networks from continuous objects. So, for example, as nearest neighbor graphs in some hyperbolic space. So for us, the inspiration for treating graphs as continuous objects actually came from the work of Ron Levy, who worked with Gita, who is present here on this call. And the way that we think in this PDE-based approach is a graph having, in addition to the feature coordinates, also some positional coordinates. So you can say that I embed my graph in some space, doesn't need to be Euclidean, can be, for example, hyperbolic space. So I have a joint space where I have positional and feature coordinates. And this is very similar to what has been done in image processing by Ron Kimmel, for example, in the Beltrami flow, where you model an image as a manifold that is embedded in positional and feature, right, or color space or texture space. And you evolve both. So you run some non-Euclidean diffusion equation called Beltrami flow that minimizes a version of the actual energy called Polyakov functional that basically changes both the positional coordinates and the feature coordinates of this embedding. So in images, the positional coordinates are a nuisance, right? So it's just reparameterization, so you don't care about them. But in our case, we can care about them because if, for example, two nodes in a graph become closer in the positional component of the space, you can say that to facilitate the flow of information, I can introduce an edge between them. And this is something that in images doesn't exist because you have fixed connectivity. And I have an image. Let me try to show it. Something like this, right? So here we have a graph. It's a Cora network. So the task here is node-wise classification. Every circle represents a node. Colors represent the features, and the positions represent some positional encoding. And you can see that here we have three things happening at the same time. So the feature diffusion, right? So the colors are changing. Positional coordinates are also changing, right? So these nodes drift apart, and also the graph is changing on the fly. So we are rewiring the graph based on the proximity of the nodes in the positional space.
Yeah, I think that's a beautiful example of all the things that one can do on graphs and with graph learning. Do we have more questions?
I think Volker has a question on Zoom.
Yes. Hi, Michael. Great talk. I mean, a lot of these plots sort of look brain-like, and I think in the brain, as you also mentioned, like symmetry, like in convolutional networks, also plays a big role. But then there's also a lot of modularity. So do you have a good idea or principled way of like working on this tension between modularity and symmetry and how they interact?
Yeah, so it's also a good question. So another physical principle, right? So if you think basically what makes physics run and work, so one of them is symmetry, and well, this is what I was talking mainly about. Another one is scale separation. So probably the compositionality, right, and the pooling that is used in convolutional neural networks is a good manifestation of it, and we can actually show that the combination of both translational invariance and pooling is what makes convolutional neural networks so successful. So that was shown by Joan Bruna and Stéphane Mallat in 2012. So they studied the geometric stability of convolutional neural networks, and the main idea is that obviously this model of group action is maybe a little bit naive abstraction, right? So it's you have more general transformations. So what happens when you subject your input to a transformation that is not exactly a group, right? So what happens to the output? And what we want is some form of approximate invariance or equivariance. So when I have an order of epsilon distance from my group, right? So approximate translation, right? That warps a little bit the image. I don't want something output effects of order of 1, right? So I want it also to be order of epsilon. Now, Fourier transform, for example, doesn't have this property, but scattering transforms, right, or convolutional neural networks that are more or less the same do have this property, right? So that's one of the motivations also for multi-scale representation for the development of wavelets.
And in terms of coding or in compression, so can you sort of compress the information in these? I mean, the net you're showing, for example, right now. So is it also like a very good way of compressing information somehow, working with symmetries, I guess, imply some sort of compression?
So compression in the sense that probably that you have less weights, right? So this is what, well, nowadays I think it's challenged by transformers just by throwing gigantic amount of data. But really what made the breakthrough in image analysis with convolutional neural networks, or maybe previously with neocognitron, is the idea of weight sharing. That can be, if you write it down as a matrix, so this is a circulant matrix, that is exactly a convolution. So you have, and well, the motivation is that if the pattern appears somewhere in the image, then you have the same rule that is captured by these by these weights that is applied anywhere in the image. So
okay,
thank you. Activity and weight sharing.
All right. I think there's no more questions at this point. Then I would like to thank Michael on behalf of all of us. Thank you, Michael, for being here with us today. Thank you for giving a wonderful presentation, and thank you for staying for the discussion afterwards. And I'd like to also thank the audience for a lively discussion, both the YouTube and the Zoom audience. So
Thank you
thanks a
very much.
lot, and it was a great pleasure for us.
Thank you. Thank you.